Welcome to this course on new lectures, and last time we just started a circle diagram of a 3-phase induction motor, and as a prelude to this we just verified that in case of any R L circuit, okay, and if it is excited by a fixed voltage at fixed frequency, and if suppose the resistance is varied from say 0 to infinity, then the locus of the tip of the current phasor will be a circle, and diameter of the circle will be V by x, where x is inductive reactance. And also note that this point is r equal to 0, because if r equal to 0, that is this is shorted, current will be V by x lagging V by 90 degree, and this point is r equal to infinity, when impedance of the circuit will be infinitely large, current drawn will be 0, and so this will be the locus, and this is the position of the tip of the current phasor for a finite value of r in between 0 to infinity, and this we have established. Now, this particular thing can be then applied to obtain the circle diagram of the induction motor. So, we will start first with a 3-phase induction motor, having no stator impedance, and also no stator loss, So, that is the equivalent circuit is like this, x 2 dashed, and this is r 2 dashed by s at any slip s, and this is the per phase applied voltage. In fact, sometimes as I told you, to get quick estimates of the performance of the induction motor, people may resort to this equivalent circuit, which is very simple, and for that we found out those things that electromagnetic torque at any slip is equal to k s alpha by s square plus alpha square, and the slip at which maximum torque occurs is r 2 dashed by x 2 dashed. These results are very important and interesting, and also T max is equal to k by 2, where k is a constant, depends on the per phase voltage, reactance of the rotor and synchronous speed. Okay. But for this type of equivalent circuit, I want to record the current I 2 dashed, and I 2 dashed will happen to be then equal to I 1 itself. This is equal to I 1 itself, because I have neglected all the things on the stator side. So, here it looks like, depending upon the value of the slip at which machine is operating, the tip of the current phasor will be located, and here it is the same case as that of this, where r is varying as slip will vary. Range of slip is between 0 to 1, we know that. Achha. Therefore, we expect that the circle diagram of the induction machine will be somewhat, suppose this is the voltage phasor V 1, supply voltage per phase, then the diameter of the circle will be at 90 degree apart like this, and the locus of the tip of the current will be here. So, this length is V by x 2 dashed. and it will, and depending upon the value of this slip, current phasors will be located. Okay. Now, we have seen that for motor operation, range of operation, I mean range of S is between 0 to 1. Therefore, S equal to 1 corresponds to the starting condition, standstill condition. Suppose S equal to 1, if S equal to 1, meaning that standstill condition, the current drawn from the supply will be suppose located here. Suppose this is the current drawn. Let this point be called O and this point let us call capital S. This will be the operating point on the circle diagram, and this is the power factor angle theta 1 say. Now, this point therefore is corresponds to S equal to 1, standstill condition. Mind you, applied voltage is rated value. Okay. So, this is the thing. Now, what you do is this, you drop a perpendicular here on this diameter of this one. Suppose it is SM. Okay. Now, as you can see, the input power to the circuit P input from the supply side will be 3 V1 I1 cos theta. I1 in this case is equal to I2 dashed is the length OS. Therefore, I1 cos theta 1, this is also theta 1 is your SM. So, P in will be equal to 3 V1 and for I1 cos theta 1, that is OS cos theta 1, it is nothing but this cos theta 1, and this length will be, this will be the length SM. See, it is a graphical method of solving, because if I know the parameters, I can use these equations to predict the performance for various values of slips. Now, we are trying to tell that you can lessen the burden of computation by once for all drawing a so called circle diagram of the induction motor. That is the main point. So, it is at S equal to 1, this is the thing. Therefore, as you can see, this P in V1 is constant per phase applied voltage. Therefore, the length SM will be also a measure of the power, is not. Although SM is current scale we have chosen, we have drawn this circle based on current, but if I know what is OS cos theta 1 is not, that is SM, it will be into V1 is gives you also power. So, in some other scale I will choose and say that the length SM represents the input power in this case. So, this is the power input. Power input when? At standstill condition, at standstill condition. Okay, fine. Now, if the rotor is not allowed to move, this will be only this situation. So, this is the total input power. Where this power goes? This power in wattage will be consumed in R2 by S only, is not S equal to 1. So, at S equal to 1, slip equal to 1, this will be the air gap power, and this itself also will be the copper loss in the rotor, and there will be no output mechanical power because rotor is not moving. So, everything is fine. Input power, that itself becomes your air gap power. S into air gap power is loss. So, S equal to 1. So, anyway that represents. So, Sm, the length Sm is the air gap power also, air gap power. And also this is equal to rotor copper loss, since small s equal to 1, and output mechanical power is 0. How much is the torque produced? Torque developed in an induction motor is nothing but air gap power, that divided by 2 pi ns, ns is constant. Therefore, Sm also represents, since it is air gap power, also in some other scale will represent torque developed or torque in synchronous watt, is not. So, everything is at S equal to 1, this is the picture, nothing else, and output mechanical power 0 in this case, P gross mechanical is equal to 0, I am sorry, P gross mechanical is equal to 0 at S equal to 1. This everything is at S equal to 1. Okay. Now, motor will be operating at some full load slip, okay, say maybe 4%, 5% of slip. Therefore, as slip value will be present, which is a number less than 1. So, whatever slip value you assume, you see that R2 is increasing, is not R2 dashed, let me write, correct it, R2 dashed by S. S is some finite value, and it will then be located somewhere here perhaps. So, the operating point P is at slip S, this is the value of the slip. At that point, what is happening? How much current is drawn from the supply? With red color I will write this, all these things associated with the general operating point P. That is it will be and suppose this angle is theta, theta 2. Therefore, OP is the current drawn, this length will represent the current drawn by the machine when the machine operates at slip, operates at slip S, general value of slip, it operates, OP is the current drawn, this length will represent the current drawn. You can see current drawn becomes lesser, because earlier it was OS at standstill condition, now it is OP. It is expected to be, because S has decreased, impedance of the circuit has increased, supply voltage fixed. So, this will be the thing. Now, what we will be doing? We drop a perpendicular on this, once again on the diameter, and let this be called P n. Then the at slip S, power drawn from the supply, power drawn from the supply is V 1 OP, that is the current, into cos theta 2, cos theta 2. Theta 2 is also this angle, because these two are parallel, which is nothing but this is equal to V 1 P n. So, these vertical drones can be used also to represent power, because it is multiplied by a constant capital V 1. Therefore, P n in some other scale is equivalent to power drawn. Is not? And if you want to write total power, multiply with 3 as we did here. V 1 is the per phase voltage. So, P n is the total power drawn from the supply. So, that is also fine. So, S m is the power drawn at S equal to 1, and this is the power drawn when it is operating at any slip S. And we are talking about an induction motor whose stator impedances have been neglected, very simplified situation. But nonetheless, it will bring out the most important things that we will consider here. And only resistance present is in the rotor, there is no stator resistance. So, after you get this point of intersection, let me call to be G here, this point of intersection. In earlier case, I showed that S m was equal to the rotor copper loss. In this case, total input power is this. Acha, consider this triangle and this triangle, and bigger triangle and this smaller triangle. These two triangles are similar. Is that clear? Acha, now copper loss, let this diagram be present, otherwise it will be difficult. Acha, I will take this ratio copper loss at S, copper loss means rotor copper loss, divided by rotor copper loss at S equal to 1, that is corresponding to capital S. This ratio will nothing but be equal to this length OP square, because that is the currents, into R2 dashed, divided by OS square copper loss at S equal to 1 into R2 dashed. This will be the thing, that is it will be equal to OP square, this length square by this length square, is not? It will be like that. Acha. Now, we will use one result of geometry which we have done in school days. I will just very quickly tell, that is, if you have a circle like this, take any point A on the circle and drop a perpendicular on the diameter, and this is an arc. This OA square, this length square, can be shown to be equal to, suppose this point is O is equal to this point is C, it can be shown to be equal to OM into OC. And the proof is very easy to prove. Suppose you join these 2 points, then this big triangle and this small triangle, triangle OAC and triangle OAM, they are similar, because of the fact this is 90 degree and this is a common angle in both of them, it is there. So, the third angle will be also equal. So, they are similar, they are similar. Where is the third angle? Third angle is here, this and this. So, ratios of the opposite sides of the like angles will be equal, that is what similar triangle means. Therefore, take the bigger triangle first. So, opposite side of this is OA divided by this opposite side is OM, these two angles are same OM, and this must be equal to, I have taken first the bigger triangle OA by OM. So, then opposite sides of these right angles in both the triangles are OC and OA. So, OC by OA, and therefore, it gives you this results, OA square is equal to OM into OC. So, this is a standard result, nonetheless for ready reference I have proved that. So, after you get this, we were here, we were taking the ratio of the rotor copper loss at operating point P, that is with any slip S, that is at P, and this is at S, capital S point. And we found that R2 dash cancels out. So, it will be the ratios of OP square by OA square. Now, the thing is that this OP square, if you call this point to be C, OP square will then be, because this is a perpendicular drawn from P upon the diameter. So, OP square will be ON into OC divided by similarly OA square, this is also a chord, from this I have drawn a perpendicular, it will be equal to OM into OC here. So, this ratio will be ON by OM. So, ON by OM. Okay, that is fine. Now, this ON by OM is nothing but GN by SM, because these two triangles, this triangle and this bigger triangle, they are similar for obvious reasons, these are parallel and things like that. So, in a triangle, you know, this is to this will be equal to what? GN, because this is the common angle, GN by SM, simple. So, this is the thing. Therefore, what we have got? We have got here is OP square by OA square is nothing but GN by SM. So, what is GN? Therefore, GN, this length, this line segment GN will be equal to OP square into SM divided by OS square, is not? It will be like this. So, GN is nothing but OP whole square into capital SM by OS square. Can you tell me what this quantity is? SM by OS square. SM is what? SM is copper loss, rotor copper loss, and that divided by current square is nothing but R2 dashed. So, this is nothing but OP whole squared into R2 dashed, copper loss divided by magnitude of the current square. So, it will be like this. Therefore, this is equal to GN. Therefore, capital Sm, this length represents the rotor copper loss at S equal to 1, slip equal to 1. Capital Gn is OP square into R2 dashed, then represents the copper loss at slip S. So from this we conclude Gn represents copper loss at operating point P at point P or at slip S. So, the interesting point is I have drawn this circle diagram. At standstill condition there is no mechanical power output and all power that has been drawn is equivalent to air gap power as well as that air gap power where it will go, there is no mechanical power output, everything will be lost in the rotor copper loss, that is Sm, OS square into R2 dashed. Now, when it is really operating at some slip S, current drawn is OP, that is what I get from the circle diagram. Then from the operating point P, I drop a perpendicular Pn. It cuts this slip equal to 1 line at point G. Then I find that okay, when the machine is operating with some slip S, Gn is nothing but the copper loss at that slip in the rotor circuit. That is the only place where copper loss takes place. But what is Pn? Pn is the total power drawn from the supply, total power drawn, of which Gn is the rotor copper loss. Therefore, I must conclude that Pg, length Pg must then give me the gross mechanical power output. That is the conclusion. That is, when it is operating at this point, any slip S, drop a perpendicular, it cuts it here, and this I know represent rotor copper loss, and total power drawn from the supply is represented by Pn. Therefore, the input power minus the rotor copper loss must give me the mechanical power output, is not. So, this is the very basic thing, and based on that we will next develop the circle diagram of a induction motor where all the parameters are not neglected, stator, rotor, those parameters I will take into account and draw the complete circle diagram of the induction motor in the next lecture. Thank you.